The first speaker today is Dr. Karem Sakallah. He received his B.E. in electrical engineering in 1975 from the department here at the UB, and then his master's degree and Ph.D. degrees from Carnegie Mellon in Pittsburgh. And he received his Ph.D. in 1981 and then joined a company called Digital Equipment Corporation. And in 1988, he left the company and joined the University of Michigan. And he has been there ever since. And he's now a professor there. And he published a lot. And he's a member of the IEEE, that's the Institute of Electrical and Electronic Engineers. Some of you are student members here. In fact, some faculty are members of this organization. And he spent last year in Qatar, and he is a member of the advisory board for the Qatar Foundation for Education. If you want to learn about Qatar, you can ask him afterwards. He received the Distinguished Alumnus Award for his contributions to the development of powerful and fast algorithms and their application in the verification of computer hardware designs and software programs. Today, he is going to talk about his experience from transistors, that's the hardware part, to multi-threaded software, an endless journey of discovery. So the journey is not over yet, so he's still continuing his journey in this field. So please join me in welcoming Dr. Karem Sakallah, who's coming in front of you.
Thank you very much, Dean Hajj, and thank you all for coming. It's really an honor for me to be back at AUB. I can't tell you how much AUB has shaped me, and I'm sure that as you go through your careers, you'll look back and appreciate the precious years that you're spending here as students. This is a special place. As I was listening to the recipients yesterday, I was thinking, oh my God, our presentations today are going to be boring because we're giving technical presentations today. And I thought maybe I should go and spiff off my presentation, change it, make it, add graphics to it, but I couldn't compete with Ubaida. So I decided it's too late. If you don't get what I'm saying over here, don't worry about it. The message is actually the subliminal message here, which is, and it was reinforced yesterday by several of the speakers, which is, don't do something because somebody tells you to do it. Do it because you want to do it. Do it because you have a passion for it. And that's the most joy that you're going to get. Everything else is just icing on the cake, as it were. So I actually had a version of this presentation that was a lighter version that I gave to the freshman class at Carnegie Mellon in Qatar last year to motivate them to kind of major in computer science. And then I decided, this is AUB, I'm going to remove that fluff and just give you the substance. And I hope that you'll appreciate that. So this is basically my journey, starting here as a double E major, and the twists and turns that my career took, none of which were planned. Okay? And there is a moral to the story that I hope we'll get to at the end. Just by show of hands, how many here are ECE students or ECE people of various types? How many are not? Okay, so it may not be as bad. I'll try to be as clear as possible on the things that are probably jargon that only ECE students might understand. So I started at the beginning of what you might call the semiconductor revolution, where digital technology was beginning to shape and change our world. And do you still teach power engineering here? Oh, you do? Okay. So you know, coming out of here, having studied power engineering and known about power generation and transmission lines and so on, I really didn't want to do that. And so this excited me. This was cool. This was the in thing to do at the time. So my graduate work was in a kind of arcane subfield of what we now call very large-scale integration technology. So that's what I did for my PhD, and then I went and I worked for a company that no longer exists. This is how fast our world changes. It was the second largest computer company in the world after IBM, and I worked there for 6 years, working on various aspects of VLSI design, and then I decided I've had enough experience in industry. I want to go and really do what I want to do, which is, you know, follow my passion. So I left and I went to the University of Michigan. And my first student actually was Dr. Icy over here. And I don't know what his experience was like. You know, I don't know what he tells you about me, but I enjoyed having him, and I'm proud that I made a small contribution to AUB by sending him back to you. But anyway, if I ask you, we all want our digital logic circuits, our digital devices to operate quickly. At least that was the desire back then. Now we want them to operate with very little power consumption so that when we carry them around, the battery doesn't run out. But at the time, the issue was, how can we make our designs go faster? And so one of the issues was to figure out, this is, of course, a toy example. How fast is this design? You know, what's the longest delay in this circuit? Okay. This may seem like a trivial problem. It just requires you to kind of figure out what the longest path in a circuit like this from inputs to outputs. But it actually involved a lot of physics. Everybody know what this is? No. It doesn't matter, but what it says is that you had to actually go and understand the physics of how transistors in these integrated circuits work so that you can tell when you change something at the input how long it takes to change something at the output. And then you aggregate these things and you add them up, and that's how you get how long a design path takes, and that tells you how long you have to wait. That tells you how fast you can run it, the frequency at which you run it. Okay? So that's what I did. And until we got to a point where, here I have to use my pen to show you something. So you get something like this, and you say, well, how fast is this circuit? Can somebody tell me? So here, suppose that each one of those blocks takes 1 unit of time. What is the longest delay in this circuit here? You probably go from 1, 2, 3. 7, right? 7. Somebody said 6. Somebody knows something here. So let's see if it's 7. So we start over here, right? We make a change, and that change goes through here. This is called an AND gate. For it to go through, I need to put a 1 here, right? Which will make the transition go through. I put a 0 here, it goes through. I put a 1 here, it goes through. And now I need to put a 0 here to make it go through here, but this 0 and this 1 are in conflict because it's the same input. So it actually cannot go through this path to give me a delay of 7. So that's called a false path. This was a revelation, and when we looked at it, we said, well, so how do we solve this problem? That means that we have to check the conditions under which propagation happens. And that led us into the so-called satisfiability problem. This is the first kind of bend in the road, as it were, taking me from being an electrical engineer to become a computer engineer, and later on computer scientist, and later on a philosopher. I don't know. I mean, it doesn't matter what label you put on yourself. You just follow kind of where the path leads. So how many of you here know what the satisfiability problem is? Great. It turns out I didn't know anything about it when this started. I had heard of it, but I didn't really know anything about it. And I'll come to this theme later on. It turns out everybody in computer science knows what this problem is. It's a fundamental problem in computer science, shown to be NP complete back in 1971. And there's a $1 million prize for anyone who can prove that the class is P or polynomial type algorithms and the class NP complete algorithm. If they're the same, the conjecture is that they're not. But if you can prove that they're the same, there's a $1 million prize waiting for you. So when we stumbled on this, I said, wait a minute, we can't possibly solve this problem. I mean, a lot of smarter people out there have been banging their heads against the wall to solve this. We can't do anything with this. But we persisted because I had a stubborn student. Another theme here is if you're stubborn but you're right, keep at it. If you're stubborn but you're wrong, then watch out. So I'm going to just walk you through, and I promise you that even people who are not experts in this field will understand in the next few slides what I'm doing here. Okay? Anybody have a problem with logic and, or, and not? You've done this here? Yeah? So this is all you need to know. We have and, which is the usual connective in natural language. Something and something means that both of them must be true. Or something and not. This is the basis of all digital logic. This is the basis of everything that we do in digital logic. And what we do then is if we take a formula such as this, A or C, B or C, not A or not B or not C. I want to satisfy all of them. How do I satisfy all of them? Let me give you some nomenclature here. We'll refer to each one of these as a clause or a sentence, and each one of these as a literal, as either a positive or a negative literal. And I can show you with a color code, which is red for 0, green for 1, and yellow for neither, how we're going to go about satisfying this set of requirements, if you will. I need to satisfy this and this and this and this, right? So if I have one of these clauses, both of whose literals are red, that means it's violated. And if one thing is violated, the whole thing is violated. Because if this is not true, then if you AND it with everything else, it will still be not true. If any of these has a green literal, that means it will be true because it's an OR, regardless of what the others are. And if you have something that has no greens and a mix of yellows and reds, that means it could go either way, depending on what I do with the others. So how do you go about solving something like this? Suppose that I give you a set of these and they need to be satisfied. The question is, can I find 0, 1 values for these variables to make each of them green? Can I satisfy all the constraints? How do we solve it? Well, one way is to list all of the possible combinations. Here we have four variables. That's 16 combinations. I can evaluate all of this for the 16 combinations and check if anyone would satisfy everything. That doesn't work for very large problems. And today we solve problems that have hundreds of thousands of variables and millions of these clauses. So that obviously does not work. This is where the exponential complexity comes in. We can do algebra. I can try and simplify this. In this case, it's trivial to simplify. But again, if you have a million of these, simplifying algebraically is not an option. Or you could do it by smart search, as it were. This is what works remarkably well. So let's do some search here. So I pick a variable A and I make it 1, green. And you see that where it occurs, that particular constraint gets satisfied and we're done with it. Where it occurs with a negation, it basically drops out, and then I have to worry about the others to figure out what's going on. So I can go with A, then B equals 1, then C equals 1, and then D equals 1. And here, what happens is I satisfy everything except number 7 over here. I need to go back a little bit here. So number 7, with that assignment 1, 1, 1, 1, I got one of these constraints got violated. So obviously, this cannot be a solution. What you do, you back off from the last decision that you made. You go back here and you try d equals 0. You satisfy a whole bunch of others, and this time something else gets violated. Okay? So what this says is that when A, B, and C are equal to 1, it doesn't matter what D is. I'm not going to be able to satisfy my requirements. So you backtrack again, and now this will animate by itself. And you can see that this is a systematic way of exploring all 16 possible combinations. In the worst case, you will actually check each of them explicitly, but in many cases, you might be able to do it with a lot less work. Okay? This is how I learned to do PowerPoint, by the way, about 12 years ago. This slide is 12 years old. And I have made enough use of it to justify the effort I put into it, which was a week worth of work to do the slide with the animation. It's not as fancy as Ubaida's, but I think it's pretty cool. We need to turn this into 3D, if you can help me with that.
You need to add commas.
Commas. Okay. So actually, the trick with this was to have a small enough example that I could put on one slide, and then I can illustrate the improvements in this algorithm later on. But you see, we did find a solution over here, which is 0, 1, 0, 1, that actually satisfies these requirements. And in fact, it is the only solution. So if I had guessed, or if somebody whispered in my ear that this is the set of choices that I had to make initially, I could have found this solution very quickly. But nobody whispers in our ears. You know, the age of revelation is gone. You know, it's way back. And so whatever decision sequence you choose, you will end up doing a lot of work before you find the solution. Worse yet, if there is no solution, you end up having to explore every possible combination to show, oh, these are inconsistent, there is no solution. So can we do better? And the answer is yes, we can do better. We can start the same way as before. But the moment we get into a situation where one of these requirements has a single yellow and everything is red, there is only one way to satisfy it. So there is no point in making an arbitrary choice here. To satisfy 7, I have to make d equals 0 for this to turn green. And that's called an implication. So that's what we do. Oops. Forward. So we start building some reasoning into this. When B and C were 1, because of 7, D must be 0, and then if I substitute this into 8, I get myself into a conflict situation. So I have avoided making a decision on the fourth variable because I inferred from what I did before what that variable should be valued at. Okay. You carry this forward, and what you see, and again, I want you to just stay with the big picture over here. If you remember that diagram on the previous slide of how much work we did to find the solution, here we are finding the solution with many fewer arbitrary choices, many fewer conflicts, and we find it much more quickly. Okay? This was all known. This was done in the early 60s. It's called the Davis-Putnam algorithm. But can we do more? And this is what we did about 12 years ago. We said, all right, well, we can proceed to make these arbitrary decisions and then follow the consequences of those decisions. But no matter what decision sequence we come up with, we might end up with a conflict situation like this. And the question is, do we just throw our hands and go back and figure out what to do from scratch, or can we learn something from this? Can we learn from the mistake? And that was the revelation. We called it conflict diagnosis. We end up with a situation where we violate one of our requirements, and we can go back and analyze it starting from the point where it's a conflict, go back here and say, well, this was really because B and C were set equal to 1. That gave us, the formula was negated, basically. It gave us a 0 of the formula. So if we turn this around, we know that the formula should have contained a requirement like this, which is not B or not C. Had this been there, when I made B equal to 1, implication would have forced C to become 0. And I would not have myself in this situation. So now we learn new facts. This is called learning now. And if I add this piece of information to my set of facts that I started with, I might actually learn to avoid the same mistake again. I would not repeat it. Learning from mistakes. All right, so we can do this and finally find that the culprit in all of this was the fact that I started with A equals 1. Any completion of that solution, A equals 1, is always going to be a conflict. And this was learned actually after 3 conflicts. We discovered that A must be 0. And A must be 0 implies that we have to actually start looking on the other side of this tree over here, and we can find our solution much more quickly than even before. Okay? The take-home message from this is we did a little bit of thinking that was way beyond what people who have been thinking about this problem for 40 years, and even though we were coming out, as it were, from left field, we're not the experts in the area, we were actually able to solve a problem that people who had been thinking about it for a long time were not able to solve. Okay? Come back to that theme. So this is all data, but I just wanted you to see that it was revolutionary at the time in that we were able to take very large problems, 26,000 variables, 91,000 conflicts. We would solve them back then in about 12 seconds. And since then, the technique that we developed, it was in an algorithm that we called GRASP, fired up a whole bunch of people all around the world, and there's now an annual competition to see who comes up with the next best solver that will win a prize, which consists of a T-shirt and a little plastic trophy. Okay? People are fired up. We get like 20, 30 submissions every year for this competition, and from all over the world, including some from the Middle East, but from a place that's a little south of here. Okay? So this was kind of the first bend in the road in my journey, and it kind of moved me away a little bit from the original application, and it started me thinking about other applications for this. Symmetry manifested itself actually in a very real way for me. This was the housing complex we lived in Qatar last year, and this was the place this is the house we lived in. But for the first 2 weeks, I would always go to this one because they were numbered exactly the same. It was number 8. This is 8, this is 8, this one is 8, and that one is 8. And, I always got confused, okay? How come? Because symmetry confuses. Okay, so what? Symmetry is beautiful, but it frustrates locating what you're looking for, i.e. searching for, especially when there's an astronomical number of symmetric configurations. If you're in a space where everything looks the same, right, then you're not really sure where you are. And we've discovered that, I don't want to get ahead of myself. So symmetry actually is one of the reasons for this huge interactability, the fact that you have complex problems that cannot be solved very easily. Search, everybody's familiar with search now. Everything we want to do these days, we just go and Google, and we do our homework that way. We prepare our lectures that way. We, without Google, I don't know what life was like. It's unimaginable. What we were doing before Google. So searching in large amounts of data is something that has become quite commonplace. The kind of search I'm talking about is not Google-type search, but we're searching in these combinatorial spaces for patterns, and if these combinatorial spaces are symmetric, then that search becomes much, much more expensive. All of the stuff that I told you about before would still not work. Here's a graph. Let's look at some of the symmetries of this graph. If we reflect it around the vertical axis, we can see that 1 maps to 1, 2 maps to 2, but 3 and 5 swap, and 4 and 6 swap. Okay, that's called the symmetry of the graph. It's a permutation of the nodes that leave the graph the same. Okay, I can rotate it, right? And I get another permutation. Now 1 maps to 4, 2 maps to 3, 3 maps to 5, and so on. That's another permutation that leaves it the same. So you go from the beautiful flower and the butterfly, and you say, what is symmetry mathematically? And symmetry mathematically is a transformation of an object that leaves the object essentially unchanged. And in fact, there are 6 symmetries of this little graph. If I just distinguish these nodes with colors, you can see that the colors move, but the graph looks the same. So what is this? It's the internet backbone from a few years ago. It's got about 285,000 nodes, about 429,000 edges, and it has 1.29 times 10 to the 83,687 symmetries. I can't imagine what this number is, right? But we found them in 0.4 seconds. Now, every time I look at this, I am impressed. And I think that the student who did this was just making this up. But it's true. We actually were able to do this, right? Now, going back to this problem that we started with, which is we're doing timing analysis of VLSI circuits, and all of a sudden we're doing SAT, and now we're doing symmetry. What the heck are we doing? If we take a formula like this, A or B, not A or not B, and C, we can turn it into a graph. Every one of these is a square node, and each one of the literals is a circle, A, not A, B, not B, and so on. And then we draw edges that represent the various clauses. So this is A or B, connects A and B. This is not A or not B, this is etc. Once we get it into a graph, we can then turn the graph symmetry tool to figure out what the symmetries are over here. And we find that there are several of them. Okay, just trust me that we can find the symmetries of the graph that leave the graph unchanged, and all it's doing is just moving around the various vertices. Okay. When we do this, we are able to add a mechanism to this search I was telling you about that will remove the symmetries. We call it breaking the symmetries. So you can mark an object in such a way that you pick one unique representative from each symmetry. So on those 4 houses that were symmetric in that housing complex, I would say my house is the representative. So I would mark it differently from the other 3 that are symmetric with it. And then I would essentially eliminate the other 3 from being even visible when I'm looking for something. And that reduces the number of things that I have to search for exponentially. Then, by adding symmetry detection, which is this process of finding the symmetries, with symmetry breaking, which is filtering out things that are similar to each other, we are able now to solve problems in hardware and software verification that were just impossible to do just a few years ago. And this turned out to be an extremely intellectually stimulating exercise. Again, like with satisfiability, I had nothing. I knew nothing about how to do symmetry mathematically. I mean, everybody has an intuitive notion of what symmetry is, but it's a very dry mathematical subject, it turns out, called group theory. And I still don't understand all of group theory. It's abstract algebra. But if I didn't at least tip my toes into that, pond, we would not have been able to solve a problem in symmetry detection that, again, people who have been doing this for many eons were unable to solve. This problem, symmetry detection, is referred to as the colored graph automorphism problem, the problem of taking a graph, like I was showing you the internet graph, and finding all of its symmetries. The best algorithm that was out there would not have been able to solve that internet graph. It was just too big. But we were able to do it. And let me show you some data here. These are examples from a variety of, let me give you an example that might be concrete for you. these are the road networks, for example, in the state of California. If you draw the graph of all the roads in California, that would have 1,679,000 intersections, if you will, and that many, well, that's it, that many intersections. And this is how many symmetry generated. This is not the number of symmetries. This is how many basic symmetry components in it there are. And we could find all of those symmetries in less than a second. Once it's a graph, it doesn't matter where it came from. Of course, we're not interested in the road network in California. We're interested in solving problems in hardware and software verification, for example. But this just shows you how we are able. We got 1,000,000x speed up on algorithms that people who have been doing this for 50 years. And the last kind of turn in this path is this business called satisfiability modular theories. Now, I'm writing over here a bunch of equations. Don't be scared. All I want you to think of is the big A's are these Boolean things, 0, 1. But the other things, think of them as equalities or inequalities involving integers. Okay? So this one here says U plus V must be greater than or equal to 12. And this one here says X must be equal to Z plus 5, Z plus 5. This generalizes this notion of satisfiability to actually include any type of constraint. And you can model just about any phenomenon mathematically with a set of constraints. People have been struggling with solving these kinds of things. If you remove the Booleans from this, this is a typical example of what they work on in the field of operations research, when they do planning, when they do scheduling, and so on. But when you add these Booleans and then you add logical operations like ORs and ANDs, this becomes a mess, and they didn't know how to do it, or they didn't know how to do it efficiently. So we are able to actually take this. I'm going to skip a little to show you how we can take these more general systems of constraints and solve them efficiently. So we're going to take this. We did not come up with this name, SMT. This was coined by some researchers at SRI International. And I had a student who was working on this, and by the time we published this, they had beat us and had come up with a very fast solver that does this, that they called Yikes. They just beat everybody. And then Microsoft saw this and grabbed this fellow, and now he is a researcher at Microsoft. They're using this now for software verification of various Windows products. So what you do is you take this very complex system of mixed constraints, and you do what we call a propositional abstraction. So you go back and you say, whenever I see one of these guys, this will either be true or false. For values that I plug in for U and V, I will either be greater than or equal to 12 or less than 12. So it's a predicate. I can replace it with a fresh Boolean variable. I here called it B. And then I can solve this using SAT, using the stuff that we did 12 years ago. And I just need to link those handles, if you will, to the actual constraint that it corresponds to. And so we separate the problem into a Boolean backbone. And if that Boolean backbone turns out to be infeasible, unsatisfiable, I don't even have to touch the other stuff. There is something in the structure of the constraints that says, it's unsatisfiable regardless. But if it is satisfiable, I need to take the constraints that were identified in this solution, pass them on to a linear solver or an integer solver, have that check them for me, and if it's satisfiable, then I'm done. Otherwise, I have to go back and refine my abstraction. Again, don't worry about it. The thing that you should think about here is how different ideas came from many different places to come up with a solution that nobody would have ever thought of before. Which brings me to my last couple of slides. As of about 3 or 4 years ago, the semiconductor companies Intel and AMD and so on, HP, ran out of ways to actually speed things up. Remember, I started by telling you that we were concerned about 20-some years ago at making things fast. Well, they kept pushing fast until it became obvious that the power requirements would make it impossible to keep going on that path. You go to about a gigahertz, 2, 3, 4 gigahertz, and then the power consumption and the amount of heat that is generated in a very small piece of silicon becomes such that you can't keep going. So they started going parallel and reducing power. And now you can buy things like in my laptop, there is a dual core machine. Now they have 4 cores and so on and so forth. So the idea of parallel computing, which has been around for a long time, is now real. I mean, we have these things. It's not a machine that is in a big room as big as this room, where you have to have specialized people do. We have actual parallel computers that we carry with us. And with parallel computers, you start running multi-threaded codes. I ran into this article, it's a one-page article the other day, and now I make every one of my students read it. The importance of stupidity in scientific research. This was written by a biologist, I believe, a microbiologist. And it made me feel good, because the way I approach the world is I am not afraid to say I don't know something. I am more worried about people who claim to know something who in fact don't. And this gave me comfort, because this is a very famous microbiologist who says, he calls it actually productive stupidity. This is a quote I pulled out. Productive stupidity means being ignorant by choice. It means focusing on important questions puts us in the awkward position of being ignorant. One of the beautiful things about science is that it allows us to bumble along, getting it wrong time after time, and feel perfectly fine as long as we learn something each time. So that's kind of the bottom line, is that you have to learn from it. Okay? But you're not afraid to say, I don't know. But you keep the curiosity, so that you keep digging until you figure something and you know. I think if we have more people in the world who are ignorant by choice and admit it, as opposed to dogmatic people who are ignorant by design, not by design, who are ignorant without knowing it, I'm worried. I get afraid, scared of these people, who are certain about certain things. And so, some parting thoughts. I graduated a long time ago from here, and I must say that a lot of the stuff that I learned over here did not seem to figure prominently in anything that I did afterwards. It's not the specific things, but it's the kind of mindset of being a free thinker, of being somebody who is curious all the time. I think that stayed with me. And if that wasn't the case, then I would not have been able to actually sustain myself, because things kept changing on us. I mean, what I'm teaching right now, I learned along the way. I'm teaching material to students at Michigan that I did not have any undergraduate or graduate training in. Okay? So don't stop learning. The diploma is not the end of the world, right? Now this is in computer science. Computer science literacy is essential for us today. So whether you are ECE or an engineer of some other type, or someone in the humanities, this has become a technology that is essential for existence. And we all drive cars, for example, and we certainly don't need to know how the engines work, but we need to know how to drive the car. We need to know, how to operate the controls and so on. So using this technology and understanding enough about it so that you can use it effectively is essential for being successful. And the most important asset, so I apologize if I'm kind of talking down to you here, this was for freshmen, is your brain. Use your brain, because it will serve you well. I use this also with my son. He doesn't like it. And the most important skill that you need is problem solving. We are in universities, not in vocational schools. In a vocational school, you go to learn a trade, to learn how to do something specific and to do it well, and to do it for a long period of time, the same thing. The kind of education that you're getting over here is not vocational training. You are being trained to become a problem solver so that as technology changes, as the world around you changes, you are able to adapt and to be as effective, 20 years from now as you are today. Plus, you need to have good communication skills. I spend a lot of time with my students teaching them how to speak and how to write. Good people skills, a sense of humor, don't take things too seriously, and to be a good citizen, to use your knowledge and expertise to make the world a better place to be for all of us. So, this was a brief glimpse of my journey. I would not have changed anything. Well, there are a few things I would have changed, but the general theme of it, which is the excitement of discovery, the curiosity about the world, the ability to meander, if you will, and to say, this is really interesting, I'd like to learn more about this, and go for it, I think is something that is, as they say in that commercial, is priceless. Thank you. So good luck on your journey, and thank you for paying.
Psychology. Thank you, Dr. Sakallah. This is a very stimulating presentation, and I followed everything. And the conclusion is very good about the people who claim they know everything that they don't is dangerous. And this unfortunately applies to some world leaders these days.
Yes, we have a few of them around, yes.
That's a problem. Are there any questions from the audience?
Why is it the importance of stupidity, not the importance of ignorance?
No. You don't want to be ignorant. You want to be stupid by design, meaning that you admit that you do not know something well. Semantics now. No, stupidity is the child's kind of view of the world, It's not ignorant. The child obviously is ignorant, but they are stupid to the point where they don't realize, for example, that what they think is correct is actually correct. You understand what I'm saying? Children have no... I tried to learn the piano when I was a little older, and I became so self-conscious that I couldn't do it because I was afraid of making a fool of myself. If you're not afraid to make a fool of yourself, then you will learn. That's I want to just give, can you get my slides off? Just give a little ad here. I want to tell you a little bit about what I did last year, just quickly. This was the assignment that we had at coauthored Foundation. And I actually wanted to give you a more up-to-date view on this, but things have not moved as fast as I would have liked. They wanted to establish a research institute that would help, nurture a culture of research in the Arab world, starting in Qatar. And we proposed to them معهد الخوارزمي لعلوم هندسة حاسب والمعلومات. How many of you know Khwarizmi? Everybody here? Yeah. It was a little shock to me that the students at Carnegie Mellon Qatar did not know what Khwarizmi was. I had to tell them. By the way, this is Russian stamp, Soviet-era stamp, because he was born in one of the republics that was now Kazakhstan, yeah. And anyway, they took to this and they're excited about it and so on. So, Professor Aisi knows about this, and I will feed him, information as it becomes available. At some point, they're going to be looking for people to actually go and become researchers at this place. And you know, this is as good a place as any to actually recruit people who can become, you know, world-class researchers that will put, you know, we have had a history of innovation in the past, and it's a shame that, you know, the other civilizations, the other, you know, countries around the world are now rising up, and I find that we are lagging behind. You know, the Indians are doing it, the Chinese are doing it, etc. It's time for us to do it.